Hello, class. We are now going to tackle the functional group of amines and looking at their reactivity. And there are many amines in nature. Like this molecule right here is dopamine, which is responsible for our mood and neurological sciences. That's a really big one. You can see it has a primary amine right here. And I'm going to review shortly how I know that's a primary amine. Any idea what this molecule is right here? This one is cocaine. And you can see that there's one nitrogen atom right there. And you can see that right now it is a tertiary amine. And as a forensic scientist, I know a little bit about cocaine because it's a pretty prevalent drug in our society. But there's a difference between cocaine, crack cocaine, and all these different versions. And it all comes down to this amine right here, if it's protonated or not. If we protonate it with some acid, what do we get? We get a positively charged nitrogen atom, which then can form a salt. When we take off the proton, when we take off the proton, what do we have? We have the lone pairs. So now it's basic. And there are many, many other examples of amines in biology, nature, natural products. Now, let's review how we know, or how do we calculate the degrees of an amine. Well, first, let's take ammonia, which has 3 hydrogens. That has no number classification. It's just ammonia. But the moment you start adding a alkyl group, represented by the R, we just count how many alkyl groups are attached to the nitrogen. And we see that there's one alkyl group, so that's primary. And if I do something like this, there's 2 alkyl groups, secondary. And I'm not doing the geometry of these molecules very well. Let's get a little bit more. Let's be a little bit more consistent here. H, R, R. So that would be secondary. And that's tertiary. And then you can have a quaternary amine. Let's see here. We'll draw it like this. Now, if you like that, that's a quaternary amine. So when you go back to dopamine, you can see this nitrogen is attached to just one carbon, so that makes it a primary. And when you look at cocaine, this nitrogen is attached to 1, 2, 3 carbons, so that would be tertiary. So the next thing that we're going to take a look at is nomenclature. Actually, before we get to nomenclature, let's just look at broadly how do amines react. So they can react in 2 ways. Let's draw some R groups here. The reactivity of amines has to do with the lone pair. That's where the electrons are. And so it can react in this manner. Take the lone pair, go like that, and then we would get something that looks like that. So the way I drew that mechanistically, how would you classify this amine? How is it behaving? Well, it's abstracting off a proton. So that's behaving as a base. And what if we draw the same amine And we just draw a slightly different mechanism. What if we had something that looked like this? The lone pair comes in, not that. The lone pair comes in and attacks the carbon in an SN2 fashion here. What do we have now? That is now acting as a nucleophile. But in both mechanisms, base or nucleophile, you can see it is the lone pair that is involved in the reaction. And that's something really, really important to keep track of and realize. Now, let's talk about nomenclature. In naming amines, there's two ways that you can do it. There's a category where you'll name amines under that title, alkyl amines, and I view that one as a simple. When the amines are very, very simple, you can use this method over here. But when the amine is a little bit more complex, you're going to use this method. Let's and you're going to use this way of naming things when the molecule is a little bit more complex. So let's delve into some examples here. So what if I drew this compound right here? You can see that the amine is relatively simple. The carbon chain is really, really simple. And we could see that is a ethyl group. So in the simple method or the alkyl method, the groups are, you see they're alkyl, the YL. So that is simply, this molecule is simply just ethyl ethylamine. But could we have named it a little bit using this method over here? You bet we could. And that's just numbering it the way we're so used to seeing it, is we see that there's 1, 2. And you can see how it says alkane amines. Well, I have 2 carbons, so that's ethane. But the suffix is amine, so I have to drop the E and just add amine. Ethanamine. So that molecule can be named in 2 ways. The simple method, ethylamine, or ethanamine. Now, what if we had something that looked like this? Something like that. If we use this method right here, alkyl, so what is that group right there? That's isopropyl. Isopropyl amine. That's how you can name that molecule. But yes, we can name it in a more complex way, but you can see that it's just a simple alkane right here. Well, technically amine, a simple amine with the carbon, just really, really simple. So we could number this 1, 2 right there. So in the complex method, what could we do here? We have the longest carbon chain of carbons is 2, and we have a methyl group hanging off on carbon 1. So we could have named it 1-methyl. 1-methyl ethane. We've got to drop the E and add amine. See how there's 2 ways to doing this. Okay. Now let me show you an example then of a more complex one. Let's draw it out like here. How many carbons do we have? We have 7 carbons. Let's start right here. 2, 3, 4, 5, 6, 7. And then we have this. 1, 2, 3, 4. We have a dashed methyl right there. And let's say if we have a alcohol there, okay? So naming complex amines is kind of the same way of naming complex alcohols right here. So in this complex alcohol here, this is a stereocenter. Let's turn that there. So how would we name this? Well, we would have to find the longest carbon chain. 1, 2, 3, 4, 5, 6, 7. So what do we have here? We have substituents on carbon 2, 4, and 6, right? So we see that we have 2 methyls there, so we have 4, 6 dimethyl. And then we have the alcohol is going to be the suffix, the OL, all for alcohol, right? And where is that? We could go like this. 2, got to have the dashes between the numbers and letters. Heptane, but it's an alcohol, OL. 4,6-dimethyl-2-heptanol. Now we have some stereocenters here, right? We have a stereocenter at carbon 2, and we have a stereocenter at carbon 4. And so if we look at those stereocenters, they're both R. So we have a 2R and a 4R that we just put into parentheses like that. Okay. Now, why am I going through all this trouble to name an alcohol when we're talking about amines? Because it's the exact same process that I'm trying to make you guys make that connection. So when we have an amine right here, we do the same process, but now the suffix has to change, right? Suffix has to change to amine. So we're using the complex way of doing things, or the alkaneamine. And the reason why we're using this method only is because look at that alkyl chain. It's not a simple alkyl chain, and it's really complex. Okay. So did the stereocenters change configuration? No, they did not. And there, it's really the same way as naming alcohols. Just adding a different suffix. All right. So there's some other examples that I want to go over here. What if we had a simple one, or 1, 2, 3, 4, 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. We had something like that. 1, 2, 3, 4. Got to make sure we have the right amount of carbons here. So we have definitely butane, right? Now it could be butane amine, or it could be butanol. Which one takes precedence? Well, you got to go to the table in your book and look at which one takes higher priority, and you're going to find that the alcohol takes priority, so it has to be a butanol. So that means we have to start numbering from that carbon. So 1, 2, 3, 4. And so where is the amine? Well, it's on carbon 4, but now we don't use the term amine. What do we call that group now that it's not going to be used as a suffix? We have to use it as a prefix. And the prefix for amines are amino. So we would say 4-amino butanol. So that right there is a prefix. But when you look at this example right here, do you see that's a suffix? And so that's amine versus amino. So subtle differences, but significant differences. And that's why you have that table as a reference so you know which words to use. Okay. So all these examples were primary amines. Let's take a look at secondary and tertiary amines and how to name those. Now with secondary and tertiary amines, this you can see is a tertiary amine. You can use the simple alkyl way or the alkane amines, the more complex way. But when you look at these, the substituents look really, really simple. 1, 2, 3, 1, 2. So you could use the alkyl method. So you just look at each substituent and say, hey, that's a methyl, that's an ethyl, that's a propyl. So all you have to do is when you name it with the alkylamine method, you just need to do it alphabetical. So it starts with an ethyl, ethyl, propyl, not propyl. What do we have? We have ethyl, propyl, and methyl. What comes before? Methyl comes before P, methyl, propyl, and I'm running out of space. But you see how I just alphabetized the ethyl, methyl, propyl, and then at the end you stick amine. That's how you would name that guy, ethyl, methyl, propylamine. But you can also use this way as well, and that's something I'm more familiar with, or well, I kind of lean towards. We just need to find the longest carbon chain. And we see 1, 2, 3. And then that's 2, that's 1. So I know if the parent name is going to be propane. I know we have a methyl and we have an ethyl. So those are going to be the substituents. So we can give myself some more room here. Now we have an N-ethyl. All right. And then an N-methyl. And then we have propane. I'm going to run out of space. Got to drop the E and replace that with what? The suffix, which is a amine. Did you? We cut that off. So let's write it down here. So the suffix right here is going to be let's see. So the suffix will look like this. Because I ran out of floor space. So N-ethyl, N-methyl. Let's just erase this because I just wrote it in yellow now. So that just continues on. N-ethyl, N-methyl, propane amine. Okay. Let's see here. Might be missing something. Let me look at this. Okay. So we just need to add this 1 right here to tell us where the amine or the nitrogen atom is attached in the longest carbon chain. Okay. So that's a more complex way. So like on the exam or something, or just in the lab, people are going to refer to this molecule as ethyl methyl propylamine. That's a whole lot easier than saying this. Okay. Now, let's take a look at a a more complex one. We have, let's see here, 6 carbons. Let's do 6 carbons here. Now I'm running out of board space, so let's just do it right here. Let's see, 2, 3, 4, 5, 6. And then we have an amine right here. We have 2 chlorines right there. What other things do we have on this guy? Okay, so you can see now that this guy gets a little complex, so we can't use this method right here. So what we have to do is find the longest carbon chain that includes the functional group, because that is an amine. That's the suffix. So we see 1, 2, 3, 4, 5, 6. And I started from the left because I wanted to give the amine the lowest locate number. So 6, the parent chain then would be what? Hexane for 6. And then we just fill it in here. What substituents do we have? If we make a list of the substituents, so I'm going to erase this now. If I just made a list of the substituents, I have 2-chloro, and I have 2 of them at that position, so I'll just go like this to 2, 2. And then we have an N-methyl. We have a N-ethyl. We got the parent name, which we know we're going to have to drop the E and put amine. Okay. Do we have any stereocenters? That looks like a stereocenter right there. And so that's an S. But we can worry about that until the very end. So we've written down all the substituents. So we just start writing them down. C, E, M. So 2,2-dichloro. So that's got that one. And then we have dash because we're treating the N like numbers now. N-ethyl. Dash. N-methyl. So that's the substituent. Then it's hexane. We drop the E. We can go like this, dash, 3, dash, because we want to tell where the amine is. And then we put the suffix right there. Hexane 3 amine. Right? And then we know that we have, excuse me, since we only have one stereocenter, you can just put it in parentheses as what it is. Or if you specified where the stereocenter is, I wouldn't mark you wrong, but it would simply be what? 3S, like that. And then you have your dash right there. So that's a little bit more of a complex molecule to name, but that's how you do it. Okay. Now you will notice in some textbooks that they take this locate number for the amine and they put it right here. So this way is acceptable. Or you could have done it like this. That is saying the same thing. Okay? Let's see, is there any more nomenclature that I want to talk about? No, I think that's all we need to talk about. We can now move on to properties of amines and start learning how they behave so we can learn how they react. And then hopefully we'll get into some reactions. All right, perfect. So let's just remind ourselves, if we have an amine, I've been drawing it something like this. Right? CH3, CH3, something like there, tertiary amine. But the way I've drawn it here is it shows that it's planar. All three bonds, just dropped my cap, all three bonds are in the same plane. That is not correct because we have that lone pair there, and that's going to change the geometry. A better representation of this would be drawn more like this. Our lone pair there. We have one bond right here in the plane. And then we have a wedge for the other methyl, and then a dash like that. Now that, what's that geometry? Typically, this is going to have probably a little bit more of a slant right there. And what's happening here? It's this lone pair right here is in a big electron cloud, so it pushes those bonds out of the plane. And now we have what's called a trigonal. That's how you spell it. Trigonal pyramidal. So this shape right here kind of looks like a pyramid in the shape of the triangles right there. So trigonal pyramidal. And so that's the shape, okay? When I'm drawing amines and mechanisms and whatnot, I just do it this way just for speed, okay? But when we actually want to know exactly what it looks like this, trigonal pyramidal. And the lone pairs right here, the lone pairs are in a orbital. What kind of orbital? What's the hybridization state here? There's 4 groups. And so we would have a sp3 hybridized orbital. I'm going to pause for a second and find this cap that I just dropped. Now, another interesting thing is, what if we have a amine? Let's draw our R3, R2, our lone pair in that orbital like that. What if we have 3 different alkyl groups or 3 different groups? R1, R2, R3. But this electron cloud also counts as a electron group. So we have 4 different groups around that nitrogen. Look at what happens here. What if we have a reflection here? R2, R3, like that. Okay. So if I take this molecule, let's identify them A and B. Okay. If I took B right out of the plane, can I superimpose it on A? You see that you can't. And so what's the relationships between these? Not mirror images of one another that are not superimposable. That makes them enantiomers, does it not? So what do we have here? We have a stereocenter. The amines with 4 different groups, and a group, the lone pair counts as a group. There's 4 different. they are going to be stereocenters. Right? Now, these amines, okay, they're enantiomers of one another, but when you go to do the experiment to see if they're optically active, it doesn't work. And the reason why is because at room temperature, there's enough heat where these guys interconvert with one another, and it just happens super, super fast that our instrumentation can't detect one or the other. It's just not fast enough because they're just going back and forth. But is it a stereocenter? Yes, it is. Okay. The next thing that we want to take a look at is boiling point. So if we take a look at propane, we see propane has a boiling point of negative 42 degrees C. So it doesn't take much to get this guy to boil. But then when you attach the amine right here, you see that the boiling point increases. And then if you replace that amine with an alcohol, you see it increases even more. So ethanol has a higher boiling point than ethylamine. Now, why is that the case? Well, this guy right here has stronger hydrogen bonding. Stronger hydrogen bonding or stronger intermolecular interactions will generate higher boiling points. This also still does hydrogen bonding, right? What hydrogen bonds? Any atom that's oxygen, nitrogen, or fluorine that has a hydrogen attached to those atoms. You can have hydrogens attached to those atoms, you can have hydrogen bonding. So nitrogen and oxygen atoms can hydrogen bond. Now, when we take a look at just amines, looking at a primary amine, 1, 2, let's do it like this. And let's do 1, 2, something like this. 1, 2, yeah. And then something like that. Which one do you think has the higher boiling point? What's going to be this guy? Why do you think that one's going to be the higher boiling point? So that one has about 50 degrees C. This one right here, 34. 34 degrees. And this guy is about 3 degrees C. So what's happening here? Well, first you need to notice that we're trying to compare apples to apples. So you see how we have 3 carbons, a total of 3 carbons and 3 carbons. We're not comparing something with 20 carbons and then 2 carbons. It has to be relatively similar to see this trend. So what's happening here? More hydrogen bonding. There's 2 hydrogens. Only 1 hydrogen. So it can still hydrogen bond, but there's 2 over here and there's only 1 here. And then you can see no hydrogen bonding. Please don't make the mistake. Yes, there are hydrogens here on the methyl. Yes, there is. But those hydrogens are directly attached to a carbon. So they can't hydrogen bond because it's only these 3 that can hydrogen bond. So no hydrogen bonding in that guy. And that's why you see a lower boiling point. Another thing to note is that amines are soluble in water to a certain degree. And the rule is for every 5 carbons, 2, 3, 4, 5, you have to have at least, if you have 1 amine group per 5 carbons, it's typically soluble in water. But if I just added 1 more carbon right there, so now I have 6 carbons per 1 amino group, then that may not, and we'll just say it's not going to be soluble in water. But if I wanted to make this guy soluble with 6 carbons, just tack on another amine, and then boom, that should, in theory, be soluble. Okay. Let's clean up this board. When you take amines, typically alkyl amines, so here's alkyl amines, here's aryl amines. Alkyl amines, aryl. But generally speaking, amines are rather basic. Okay? And so because they're basic, you can protonate amines by treating them with weak acids. So a weak acid, let's say some kind of carboxylic acid. If you treat those two species together, what are you going to get? You're going to get the protonated version here. That's a methyl. And then you would tack on that 4th hydrogen, which would give you that species. All right, it's just simple acid-base chemistry here. And because amines are so basic, they can do this reaction. So what's the pKa of carboxylic acids? The pKa of that guy is about 5, and the pKa of this guy is about 10.6 or 10-ish. So you see at equilibrium, what side's going to be favored more? The products, because we go into the direction of the weaker acid. That's not the right arrow, is it? It's going to be favoring this way, like that, because that's the weaker acid when you compare the two. But when you take a look at an alkyl versus an arylamine, which one do you think would be more basic? When you're thinking about that, you're basically asking how easy can we use these lone pairs to abstract an acidic proton. And so hopefully, as you're looking at this, you can see something that helps us answer that question. That's a benzene ring, is it not? And this is aniline. And what can happen? We have a resonance structure, do we not? Like so. It's an electron donator, right? It's a donator, so it's an activator. So this lone pair can donate into the ring, and it can be used to abstract a proton from an acid, to protonate it. So that would turn us into this guy right here, NH3. But then compare this to the alkylamine. When you take a look at this, can this lone pair right here resonate in anywhere? Is there a resonance structure for this? No. So all you have for this guy is it can only do one thing. It just comes in and abstracts the proton. So it is this amine that's going to be more basic because its lone pairs can only do one thing, and that's going to abstract the proton. Whereas aryl amines, the lone pairs can be used to donate electrons into the ring, and it can be used to abstract the proton. So this amine right here is going to be less basic than a alkyl amine. And this process right here of donating electron into the benzene ring is called delocalization. We've heard that word many times now. So that lone pair is delocalized, whereas that lone pair is localized. It does not move around. Okay. So just to compare here, the pKa's of this guy. What did I say this guy was? 10.6, I believe. Yeah, so the pKa of this guy is 10.6. And then the pKa of the protonated form of aniline is 4.6. Right? So when you're looking at that, these pKa values are going to tell us, hey, the base from which this acid came from is going to be more basic. Okay? Let's see here. So when we're comparing just the acids, this is a stronger acid, right? Because it has a lower value. So that means it's going to want to go this way. It wants to go this way more so than this guy wants to go back. Okay. Multiple ways to look at it. Okay, so it looks like what we're going to talk about next is we need to review and remind ourselves, how do we make amines? Okay, how do we make amines? I'm not going to write them down or go through them in detail because a few of them we've already seen. So let's just talk about this. So the first way to make amines is take an alkyl halide and treat it with sodium cyanide, which will generate a nitrile. And then you can take that nitrile and reduce it with lithium aluminum hydride to generate a amine. That's one way that you've already seen before. The second way is you can take a carboxylic acid, treat it with thionyl chloride to convert it into the acid chloride. After you form the acid chloride, treat it with a amine. So you're taking an acid chloride reacting with an amine, which will then convert that into a amide. And then you'll take that amide and reduce it with lithium aluminum hydride to give yourself a amine. So you've seen those reactions before, something to remember. Also review, how do you make aniline from benzene? Recall that you can treat it with nitric acid and put on a nitro group, and then you take that nitro group and you can reduce it. And there's many ways to reduce a nitro group. So you can form aniline that way. So those are all reactions that we have seen before. But let's take a look at some reactions that are going to be new. So what we could do is a substitution reaction in which you can take ammonia like so as a lone pair, and you could treat it with a very simple alkyl halide. Let's say methyl iodide. And you can envision what is a substitution reaction. The lone pair comes in, attacks, and kicks off the leaving group. And so what's that going to give us here? That's going to give us, and I'm just going to draw it out like this, NH3. Well, actually, that's going to be a bad idea because we've got to show the mechanism here. So there's our methyl group plus our iodine that fell off. Now, as you notice, as I'm doing this mechanism, I'm not paying too close attention to the geometry. I'm just drawing it to be the most convenient for the mechanism. And so if has 4 bonds, that has to be positively charged, right? So we can have a process here in which we have the other amine, excess of this guy floating around, and that can do a deprotonation step for us to get us our product. Let's see, we can do it like this. Okay. Now, if that's our target, and then we just generated NH4 right there, ammonium. So if that's our target that we want, we're going to run into a problem here, okay? And the problem is this. You have now a primary amine. There's still going to be some methyl iodide around. So you could envision another substitution process occurring here, like so. And that's really, really hard to stop. So you have CH3, put on our other methyl, HH, okay? And then we're going to do a proton transfer with some base around. So then we'll generate what? Well, let's just do it stepwise here. So we have a proton transfer. I'm not going to draw that guy out, which will give us this. And an H right there. What do we have? We have a secondary amine with lone pairs. It can do it again. It could take another methyl iodide here. And you can see it happening all over again. And now once you get to this part, what has happened here? Let's see here. That's going to give us 1, 2, 3, 4 hydrogen methyl, methyl, and another methyl. So now we have now we can do another proton transfer, and we would get that guy right there. But that guy also has a lone pair. It will do it again with another dose of that guy. So then now what you're going to get is a positively charged species right there. And we would call that a quaternary amine. But you're going to form the quaternary amine salt because now you have iodine hanging around and you form that salt. So the issue of trying to form an amine with a simple amine and a simple alkyl halide is you just can't stop it at what you want. So you are going to have a huge pot full of a mixture. You're going to have this product, that product, that product, and that product. And that is going to be a pain to isolate and purify. Now, if your goal was to get the quaternary ammonium salt, then you could like just dump gobs and gobs of that and just kind of just force it all to that. And if you add excess of the methyl iodide, your goal and hope is that you will react these three right here, 1, 2, 3, and just get them going all the way to this. And that's possible. But if you were like, say, I want this guy, good luck. It's not going to be very efficient. But there is a better way to make amines than this one. And this one is just a simple SN2 substitution reaction. A better way of doing it, and a reaction that I did in graduate school over and over and over again, is that you can use an azide. And using an azide is something like an azide is this, where you have a NH3 minus. And what you do is you buy it in a sodium azide. So sodium azide. And what you're going to do is if you just take a very simple alkyl halide and treat it with sodium azide, you're going to replace the alkyl or the halide with the azide, which looks like this, N3, like there, a simple azide. And then you'll take the azide and you will reduce it. Reduce it into the amine. And so we are out of time, but that's the reaction that we're going to look at next. And we can call that the azide synthesis. Okay. So we'll look at that mechanistically on how that's all going to work in the next video. And then, let's see, we have a couple more reactions that we need to talk about on how to make amines. So we're going to talk about in the next video azides. We're going to talk about Gabriel amine synthesis and reductive amination. Okay, so that's where we'll stop.